Welcome, everyone. Hope you're having a good Wednesday. Um, Today, we're going to be given a talk by Club President Nick Juricic, and he's going to be talking to us about differentiation under the integral sign. So enjoy. Feel free to ask questions at the end. Nick, I don't know if you want throughout, but
Um, Put them in the chat, definitely, yeah.
yeah.
Um,
And make sure to fill out the form that was posted in the chat and will be posted again right now. All right, take it away, Nick.
okay, thank you, Peter, for that introduction. I will indeed be giving a talk about differentiation under the integral sign. So, Keith, remember to set up the recording if you have not already. So first, I will tell you a little story. Here is a book. It's called Surely You're Joking, Mr. Feynman. It's an autobiography by the physicist Richard Feynman. So you can see here, I love this book, and I hope someday you will read it too, and perhaps enjoy it. It's a very light read, nice, has lots of great vignettes. So there's a particular chapter in this book. It's called A Different Box of Tools. I'll read you a quotation from this chapter. So this is a quote from Feynman. He says, let me adjust my screen. I had learned to do integrals by various methods shown to me in a book that my high school physics teacher, Mr. Bader, had given me. It showed me how to differentiate parameters under the integral sign. It's a certain operation. It turns out that it's not taught very much in the universities. But I caught on how to use that method, and I used that one damn tool again and again. If guys at MIT or Princeton had trouble doing a certain integral, then I tried differentiating under the integral sign, and often it worked. So I got a great reputation for doing integrals, only because my box of tools was different from everyone else's, and they had tried all their tools on it before giving the problem to me. There's this great metaphor of a different box of tools, like Richard Feynman has his own toolkit, and actually, we all have our own toolkits. So at the very least, I'm hoping you'll walk away from this talk having added at least the tool of differentiation under the integral sign to your own toolkits. So this is partial derivatives. These are going to come up in the talk. If you haven't seen them before, don't worry. If you have seen them, great. This will be some review. So we remember from a single variable calculus, you have a function f of x of one variable. We write its derivative as f prime, or use the Leibniz notation, df dx. If you have two variables, so not just a function of x, a function of x and y, you can take its partial derivatives. So the idea is the partial derivative with respect to y, for instance, we treat all instances of x in the function like a constant, and we just differentiate y as we would usually. So here's an example. The function x squared plus xy cubed, if we take the partial derivative with respect to x, see x squared, we do it like normal. The power rule, derivative of x squared is 2x. But xy cubed, we treat y cubed like a constant. It's like differentiating 5x, for instance, with respect to x. The derivative of 5x would be 5. So in this case, it's xy cubed. The derivative is y cubed. So we can do a similar thing with a y partial derivative. X squared is entirely a constant in terms of y, so its partial derivative with respect to y is 0. And similarly here, we treat x like a constant. We use the power rule for y. We get 3y squared times x, and 3xy squared, same thing. This is the notation. Instead of d, we use these little partial signs. I once heard them called thools, though it's not too relevant. There's also, so this is the example we just talked about put into the notation. We'll look at another example, though. So now we're not in x and y, but we're in the variables x and t. Can take the partial derivative with respect to t of this function. What is it? It's x squared plus t all squared. So the way we do this, take the partial derivative with respect to t, we use the chain rule. This 2 comes down, the power decrements by 1, as you see, and we multiply by the derivative of this inner function with respect to t. The derivative of x squared with respect to t is 0. Derivative of t is just 1, so we multiply by 1. So we can do that using the chain rule. another example. We're going to take the partial derivative of this guy with respect to x. So we're treating this t cubed here in the exponent like a constant. We treat x squared as we would normally when taking derivatives with respect to x. So we use the chain rule again. This constant t cubed comes down. And we end up having to multiply by the derivative of x squared with respect to x, which is 2x, as you should know. And derivative of e to the x is itself, so this remains the same. And we can do a similar thing with t here. Instead of x squared, you see it's 3t squared, x squared, e to the t cubed, x squared. So what is, okay, this isn't a cool example. What's the derivative of this? X to the power of t with respect to t. It's not, like you might expect, t x to the t minus 1. It's like differentiating, as is written here, 3 to the t with respect to t. It's an exponential, not just a fixed power. So we have to multiply by the log of 3. In this case, it's written log of 3. It's actually the natural log of 3. So for the rest of this talk, we'll be using that notation, just I should say now. And so this partial derivative is equal to x to the t times the log of x. So anybody have questions, comments, concerns? If so, spam the chat, please. And moving on, that's kind of the background knowledge that will be very helpful for the rest of this talk. This is the actual result of differentiation under the integral sign, which we're going to be talking about for the rest of our time here. So what does this say? We have an integral from a to b, not only of f of x, let's see, the variable of integration is with respect to x, but we also have this t thrown into the mix. So this integral is going to be as its integrand, some expression involving not only x, but t. You can think it's like a function of t. So we can differentiate it with respect to t. And it's kind of weird to think about, but it turns out what happens when you do that, under suitable conditions, it doesn't always work, but under suitable conditions, you can take this derivative with respect to t and move it under the integral sign. Aha. And so when you do that, it becomes a partial derivative of the inside function f with respect to t. And it might look abstract now. We're going to look at these relatively concrete examples, or at least as concrete as you're going to get when you're doing definite integrals in calculus setting. So here's one that we're going to look at, the integral from 0 to infinity of sine x over x, the integral from 0 to 1 of x to the minus, or x minus 1 over the natural log of x, the integral over the whole real line, e to the negative x squared over 2. I'm going to look at this integral from 0 to infinity of x to the n e to the negative x with respect to x for various powers of n here. But all of these integrands, except for the last one, do not have what they call an elementary antiderivative. It's really just fancy pants language for it's difficult to write down. You can do it, but it's not in terms of any nice functions that we're used to working with. So, okay, having said that, let's look at an example that isn't any of those, a more basic one, just to get the mechanics of this technique under our belt. All right, so consider the following integral. Integral from 0 to 1 of x squared plus 5 all squared with respect to x. We can do this. We know how to do this from Calc 1. The way we do it is, we FOIL it out, and then we'll apply the reverse power rule to the individual terms that we get. So we FOIL it out, we get the integral of from 0 to 1 of x to the 4th plus 10x squared plus 25. We use the reverse power rule and apply the fundamental theorem of calculus. When we plug in x equals 0, the whole thing's just 0 because we have an x in every term. So it's 0 plus 0 plus 0. We plug in 1, as you can see, we get this sum of rational numbers, which can be simplified to this if you like. So this is the value of the integral. See, it's boxed here. Very pretty, right? Okay. So what we're going to do next is we're going to tackle the same problem using differentiation under the integral sign. Come on, spam the chat. I know you're excited. So how are we going to do this? It's not a function of t here. It's only a function of x. Yes, woo, I love it. We're going to change this 5 into a t. We're going to define actually a more general integral. It's not just this one integral. It's I of t defined to be the integral from 0 to 1 of x squared plus t, all squared. And we see if we were to plug in t equals 5, we get our original integral. But at face value, this integral encodes much more than that. It's not just this one particular integral that has t equals 5. It's infinitely many. And so we'll see how that comes into play later. What we're going to do is we're going to use differentiation under the integral sign to differentiate this integral as a function of t. We're going to compute what we get for that. It's going to get a bit simpler with the algebra, and we're not going to have to FOIL it out like we did before. And then we're going to take it all back and try to pull some tricks. We'll go into that. So far we've defined this parametrized integral. So you can see how we're going to set it up right in the form of the original definition as we laid out on some previous slides. If you're a real stickler for the rules, you can see just how it all fits together. So we define f of x comma t to be x squared plus t all squared, right? So when we take the derivative of I with respect to t, we're differentiating this integral here. d dt of this integral, by differentiation under the integral sign, can move this derivative inside the integral. It becomes a partial derivative. Now we're differentiating x squared plus t all squared with respect to t. So it was actually in one of our examples before on the slide where we were talking about partial derivatives that it's equal to this. So you can just take my word for it if you're not convinced. So what now? We can do this integral without having to expand anything out like we did before. And yes. So we can do it now with more simple algebra at the cost, the trade-off, if you will. We're going to involve some more calculus. So we've established so far that this is true. When we do this integration with respect to x, we use the reverse power rule. And this is what we get when we apply the fundamental theorem of calculus. So I prime of t is equal to 2/3 plus 2t. Okay, so we've just done this integral with respect to x. Now what we're going to do, notice that this I prime is entirely in terms of t. We can integrate it now with respect to t, not with respect to x, with respect to t. And when we do that, we apply the reverse power rule, but now in terms of t, we get 2/3 t plus t squared plus our constant of integration. Don't forget it. So it's all well and good. Now we just have to find this c. And so the way we're going to find this c is by looking at our original parametrized integral here at a very convenient choice of t. So this is what we have so far. But what convenient choice of t am I talking about? Notice if you plug in t equals 0, this is 0. So it's the integral from 0 to 1 of x squared squared, the integral from 0 to 1 of x to the 4th. That can be evaluated as 1/5. If we take this information and combine it with what we have here, we can get an equation to determine c. We plug in t equals 0, we get that 1/5 I of 0 is equal to this expression evaluated at 0. And so it turns out that c is equal to 1/5. So we have our result. This somewhat more general parametrized integral in terms of t, its value can be found by evaluating this quadratic polynomial in t. We have it here again. Well, we were not originally after this more general integral. We wanted x squared plus 5 all squared. So what we do now is set t equals 5. And when we do that, we get the same answer as we did before by the more direct method. So first and foremost, I would not claim to you that this is simpler. Okay, I'm getting ahead of myself. Why stop here? We can set t equal to pi, and so we get more for, well, in this case, more. I wouldn't claim that it's simpler. This is an example problem to get the mechanics under our belt, like I said. In the future examples, it might actually turn out to be simpler to do this than to use another method. It's like a needle to pop a balloon. It's a trick that does it just right. So what is the takeaway of this? There comes a time in life, perhaps you are trying to shut a door, but for some reason you can't. Maybe you don't have the strength, or the door is just particularly stubborn. Infinite possibilities, right? Unintuitively, we sometimes may wish to open it further. So when we open the door further, we can pull it back with greater force. Okay, maybe I can slow down a little. Yes, I can post the slides later. So how to find C. So what we did so far is we found this expression for I of t. It's this integral in terms of t. And we got it in terms of t as this polynomial here, but there's also a c. So in order to find c, we plugged in t equals 0 to this parametrized integral. And we found that I of 0 is equal to 1/5. The trick to find c is we compute the original integral at 0, but we also compute this expression we found for I of t, which is the same as the integral at 0. So when we do that, yeah, okay, we get 1/5 equals this, and these are both 0, so c is equal to 1/5. I'm glad you asked, because we'll return to this trick, sure, later on many times, like in literally every example, except for one, I think. So here is another integral. It is famous in signal processing and Fourier analysis. Sine x over x integrated from 0 to infinity. Turns out it's equal to pi over 2. How lovely. So maybe it's not clear at a glance why this converges to the integral of regular old sine x on the same interval integrated would not converge. It's because this x makes things smaller. We get a bit of positive area here. We get some negative area here, but it's a smaller magnitude. You get some even more positive area here. It's decreasing. It's kind of like alternate series. You get closer and closer to some finite limit. So how can we find this? As I mentioned before, this function sine x over x does not have a nice antiderivative in terms of familiar functions. Anybody have a guess how we're going to do it? Title of the talk. Well, you know. So we're going to actually consider a more general integral. It's not just this integral with respect to x, but now it's still an integral with respect to x, but it includes this t. Yes, the physicist says to solve it numerically. It's a legit move, you know. We all have our different needs. So this is pretty tricky. We're going to attach this e to the negative tx term here. And this, I see someone says it converges slowly. This negative tx, e to the negative tx, is going to damp this graph even further, so it'll converge even faster, thankfully. So how does this relate? Yes, the original integral. So we've complicated things. However, notice that if we plug in t equals 0 here, the e to the 0 is equal to 1. So this I of 0 is our original integral that we're after. Okay. I saw another question, but I did not catch it before it disappeared. So it's not obvious how we are choosing this e to the negative tx, and we'll see in the next example, actually, that there are other parametrizations of this integral that don't work as well as this one. But the idea for this particular approach is we're going to define this parametric integral and take a derivative. And when we take the derivative with respect to t, not x, notice, we can use the technique that is differentiation under the integral sign to take this d dt, pop it inside, becomes partial t of this whole function. So the derivative of I of t, I prime of t, is equal to this integral of this partial derivative of this function with respect to t. Now sine x over x, this is a constant in terms of t. It has nothing to do with t, so we can basically ignore it entirely. We can just look at this e to the negative tx, which does involve t. So when we differentiate it with respect to t, we treat x like a constant. It's really, you think like negative x. So you differentiate e to the negative 5x, you get negative 5 e to the negative 5x. Same idea here. When you differentiate this with respect to t, we'll get the negative x that comes down, e to the negative tx. This is very good because now we have an x here and an x here. How convenient. So we can cancel them, see? And they just go away. So we're left only with the negative sign that popped out of the chain rule. So I prime of t is equal to the negative of the integral from 0 to infinity of e to the negative tx times the sine of x with respect to x. We're integrating. How is this any better at all? Isn't this just terrible? Actually, no, because unlike sine x over x, this function here, e to the negative tx sine x, does have an antiderivative with respect to x. It's very nice, and you can find it. The way we can find it is, well, a way we can find it is by integrating by parts twice. So if you have seen this, great. Otherwise, you can take my word for it. You're going to be, differentiating and integrating something. You should differentiate this e part in both steps, and you can integrate the sine. It'll become negative cosine, and the cosine, negative cosine becomes negative sine, and so on. And when you do that, you get this formula. So it involves both t and x. Indeed. This is what we're trying to integrate here. So we've integrated this I of t is this integral of e to the negative tx sine x dx. So now that we've found the antiderivative of e to the negative tx sine x, we can apply the fundamental theorem of calculus to evaluate this integral. And when we do that, it's going to help us get an expression for I prime of t. So at x equals infinity, or you could think taking the limit, this goes to 0 because it's e to the negative infinity, you think. It's plugging in a very large negative number and raising e to that power. So that first term is 0 here. We do the fundamental theorem of calculus. And at x equals 0, we get t times the sine of 0, which is sine of 0 is 0, so this is 0. Cosine of 0 is 1. E to the negative t times 0, e to the 0 is 1, so we're left only with 1 over 1 plus t squared. Since it's the lower limit, we're subtracting it off. In total, this gives us that I prime of t is equal to 0 minus 1 over 1 plus t squared. So it's just minus 1 over 1 plus t squared. I promise, we really are getting somewhere. What is an antiderivative of 1 over, or negative 1 over 1 plus t squared? Does anyone know in the chat? Arctan, awesome, yes. So 1 is the negative arctangent, since it's negative. And so we integrate with respect to t now. We're going to integrate I prime of t on this side and negative 1 over 1 plus t squared on this side. We get that I of t is equal to the negative arctangent of t plus c. So now we're in the same kit as before. How do we find out c? It's not as simple as just plugging it in this case, but well, if plugging in infinity is something you're comfortable with, then I suppose, but the mathematicians would like to be rigorous and take a limit. So we'll take the limit as t approaches infinity. And so there's two things to worry about here. We'll have to take the limit of this integral, which depends on t, as t goes to infinity, but we'll also have to take the limit of the negative arctangent of t plus c as t goes to infinity. So let's look at the arctangent part first. Here's the graph of the inverse tangent function. It goes like this. You can see it has these horizontal asymptotes. This is actually y equals pi over 2 and y equals negative pi over 2 here. So as t goes to infinity, the arctangent of t goes to pi over 2. So as t goes to infinity, the negative arctangent of t goes to negative pi over 2. But what happens to this integrand, or this, think about the integrands instead of the whole integral. What happens as t becomes very big? E to the negative t times x will become very small. So the integrand is going to look like 0 as t goes to infinity. We're happy to say that this whole integral will become 0 as t goes to infinity. Write it shorthand. I of infinity is equal to 0. If we were like, think about plugging in t equals infinity, this integral would equal 0. And so, how does this come back to finding c? Recall we have this expression for I of t. I of t is the negative arctangent of t plus c. We take the limit of both sides as t goes to infinity, and like we just talked about, when you do that, I of t goes to 0, so this side is 0. Negative arctangent of t goes to negative pi over 2, so we get a negative pi over 2 here, and c doesn't care about the limit, so it stays itself. We bring the pi over 2 here, we get that c is equal. We bring the negative pi over 2 to the other side. C is equal to pi over 2. Good so far? So we've found this c. We have our original integral, not our original, but our parametrized integral. In terms of t, we found it to be negative arctangent of t plus pi over 2 for t greater than or equal to 0. Our original integral did not have any of this e to the negative tx shenanigans. We just had sine x over x. So like we talked about before, if we plug in t equals 0, that goes away, and we find the value of our original integral. The integral from 0 to infinity of sine x over x is indeed, as shown by differentiation under the integral sign, given by pi over 2. How beautiful, right? Questions, comments, anything like that? If not, I will move on to the next example. This was a sine integral. Well, okay, I'm getting ahead of myself. Let's summarize what we did, even if there aren't any questions in chat. So we had this integral that we wanted to calculate, and we were like, geez, it's terrible, doesn't have an elementary antiderivative. We want to use differentiation under the integral sign. We introduced a more complicated integral. It was not clear how we arrived at this particular complication that was construed by adding e to the negative tx into the mix. It's not easy. It requires creativity, experience, patience, and such other good qualities as those. And we saw that it's the special case I of 0 of this parametrized integral. So that's what we wanted to find. And we used differentiation under the integral sign to show that the derivative of this parametrized integral with respect to t was equal to negative 1 over 1 plus t squared, something only in terms of t. And then we integrated both sides with respect to t. We found that I of t is the negative arctangent of t plus a constant of integration. And so we needed to find that constant of integration. We took the limit as t approached infinity on both sides, and it showed us that c was exactly equal to pi over 2. So this parametrized integral here can be written in terms of t as negative arctan of t plus pi over 2. And in order to find the value of our original integral, we plugged in t equals 0. Recall that arctangent of 0 is also 0, so it goes away, leaving us only with pi over 2. The moral of the story, unintuitively, to solve a problem, try and solve a harder problem. Okay. Now I will actually move on to the next example, which is some shortcomings of the technique. So, like I was saying before, it's not always clear what parametrization to introduce. So we tacked on this e to the negative tx, and somehow things worked out. Like, why did they work out? Why this particular trick? Well, let's think about doing another sort of thing. So instead of tacking on an e to the negative tx out of nowhere, how about we put the t inside this sine of x? It's a similar effect, right? We've still parameterized the integral with respect to t, but we notice that if t equals 1, it's our original integral, so maybe we'll just try to do the same trick and compute I of 1 at the end. If we could differentiate under the integral sign, it's like a hint, like it doesn't actually work. I mentioned before there are some conditions that need to be satisfied. We try to move the derivative inside the integral, and we differentiate sine of tx over x with respect to t. The x pops out by the chain rule, and this becomes cosine of tx, and the x's cancel. We're left with the integral from 0 to infinity of the cosine of tx dx. Okay, but it's quite troublesome because this integral does not converge. You can see that the graph just oscillates back and forth forever to eternity, and so the area doesn't approach any value in particular. Like, why doesn't this work? It turns out that this integral is equal to pi over 2. That throwing this t into the mix here does not change anything from what we did from the original integral we sought. So this function, I of t, as we've defined it here, is actually constant. We can take derivatives of it, but it's 0. But we can't take derivatives of it like this. The conditions, whatever they are not satisfied. So, okay, maybe I should have showed that here. But here's some legitimate advice. When we parameterize the original integral, some serious tact and trickery can be required. All right. Does anybody have questions so far? Comments? Anything? Feel free to post in the chat at all times. So here is another integral. Now it's not a sine integral, it's a log integral. It's the integral from 0 to 1 of x minus 1 over the natural log of x. How will we do it? You guessed it, differentiation under the integral sign. So we will define this parametrized integral. It's the same kind of thing, but now instead of x minus 1, as it is here, it's x to the t minus 1. So it's kind of weird, right? But just to get some geometric intuition, here's the graphs. So this is the graph for t equals 1, which corresponds to our original integral, actually. So we plug in t equals 1, x to the first power is x itself. And here's t equals 1.5. You see that the integrand gets a bit steeper. Thank you. Our original problem is I of 1, like I just said. You plug in 1, it remains itself x. And we know that I of 0 is equal to 0. How do we know this? It's because if we plug in 0 for t here, yes, the numerator is equal to 0, because x to the 0 is 1. We get 1 minus 1, 0. Great. So we'll use that later on. Here's our plan. We're going to take the t derivative of this parametrized integral, and then we're going to do some tricks to simplify the integral, and then we're going to integrate with respect to t, and we'll be left with a constant of integration. Similar thing to before. And then we're going to find this c using our initial condition, I of 0 equals 0. And to get the value of our original integral, we're hoping to calculate, we'll plug in t equals 1, and hopefully all will be well in the world. So we've defined this parametrized integral. We're going to differentiate it with respect to t. It's always good to remember here, we're integrating with respect to x. We're differentiating with respect to t. But we can, by differentiation under the integral sign, I prime of t is d dt of this integral here. We can move that derivative with respect to t inside under the integral sign, if you will. And it becomes a partial derivative with respect to t. Now, taking the partial derivative of this whole thing with respect to t, what is it? This 1 over log x. It's a constant in terms of t. It has nothing to do with t. So we can only or we can focus only on this x to the t minus 1 term. So we talked about it before, like Elizabeth mentioned in the chat, that derivative of x to the t with respect to t is the natural log of x times x to the t. And this 1 goes away because it's a constant. So we get x to the t times the natural log of x over the natural log of x. We have them upstairs and downstairs. We can cancel natural log of x, leaving only the integral from 0 to 1 of x to the t. Now, unlike before, we had to be careful. We were differentiating an exponential. T is a fixed power here, or fixed insofar as it's not the variable of integration, which is x. We can integrate x to the t with respect to x using the reverse power rule like we're used to. So when we do that, this is what we get, x to the t plus 1 over t plus 1. And we use the fundamental theorem of calculus and evaluate it at the endpoints. So when x equals 0, it's just 0. And when we plug in 1, we get 1 over t plus 1. So that is our expression in terms of t for I prime of t. So this is what we've done so far. We've established this parametrized integral. We've defined it, I should say. And we found when we take its derivative in t, we get this 1 over t plus 1. So what we're going to do now is integrate the whole thing, this equation, with respect to t. Integral of I prime is I. The integral of 1 over t plus 1 is the natural log of t plus 1, plus our constant of integration. Again, don't forget it. So how are we going to find that constant of integration? We observed before that I of 0 is equal to 0, so we can plug in 0 to both sides of this equation in order to determine c. When we do that, we get 0 on the left here is equal to the natural log of 0 plus 1 plus c. This is the natural log of 1. The natural log of 1 is 0. What power do I have to raise e to get 1? It's 0. E to the 0 equals 1. So this tells us that c is 0. So this goes away. Our parametrized integral from 0 to 1, x to the t minus 1 over the natural log of x is equal to this nice little expression, the natural log of t plus 1. How convenient, right? We can set t equals 1 now, and it gives us the value of our original integral. When we do that, 1 plus 1, I should say 1 plus 1, it's a natural log of 2. So how curious. An elegant method, like such a convenient cancellation that we ended up getting that made it all possible. Let's recap. We started with this integral from 0 to 1 of x minus 1 over the natural log of x. We made it more complicated. Right? Instead of just having this be x, now it's x to the t. Okay. And then we took a derivative and used differentiation under the integral sign. We eventually simplified it. The t derivative of I prime of t, is equal to 1 over t plus 1. And we used t antiderivatives. We integrated, we found that I of t was the log of t plus 1 plus a constant, and we found that constant to be equal to 0 using our initial condition. And we put t equals 1 in, we found the value of our original integral. The general theme here, and maybe the talk, perhaps even life, in order to get closer to our desires, since distance is essential, we have to give them a little space. And maybe in the end, like this integral, it'll come our way again in the future. And we actually got even more, because not only did we calculate the value of this integral, but we calculated the value of all of these integrals for any t greater than or equal to 0. All right. Questions, comments so far? Anybody? I'll move on to the next slide. So here is the Gaussian integral. It's very important. Probability, Fourier analysis, physics, you name it. It's the bell curve, the integral of the bell curve. You've heard that. So in this case, the function we're looking at is e to the negative x squared over 2. And it turns out if you integrate this function over the entire real line from negative infinity to positive infinity, it's equal to the square root of 2 pi. So it's kind of tricky to show though. Like like sine x over x and the log integral, it doesn't have an elementary antiderivative, so we can't just use the fundamental theorem of calculus in a convenient way to us. There's an old trick in the business where you like square this original integral, trying to compute it, and it becomes a double integral, and then you change that double integral to polar coordinates, and the integration becomes nicer, and you get a value, which turns out to be 2 pi. So then you take the square root of both sides. This integral squared is equal to 2 pi, and you find that it's equal to the square root of 2 pi. So that's one way of doing it. It's very nice. That's not what we're going to do, since this is a talk about differentiation under the integral sign. We're going to introduce a parametrized integral version. Well, it's not so clear, but we'll get to that. And then use differentiation under the integral sign to arrive at our result. I want to say here that this example is a bit of a different flavor from the rest of the examples in the following way. In the other examples, we defined this parametrized integral, something in terms of t that related to our original integral. And we could get our original integral back by just plugging in a particular value of t. That is not what we're going to do here. You can try to fiddle with it, and maybe you see it's not so clear what value of t to plug in to simplify this to our original integral. It's because that's not how we're going to do it. We're going to make a clever use of the fundamental theorem of calculus, and that is the main workhorse that's going to get us to our result. Of course, don't discount differentiation of the integral sign. That's at play too. So let's use the technique to differentiate I of t with respect to t. We do that. We can move the ordinary derivative inside the integral sign. It becomes a partial derivative. And we are left with taking the partial derivative of this whole thing with respect to t. It's quite unwieldy, isn't it? However, don't dismay, we'll be okay. So this 1 over 1 plus x squared can just come out. It has nothing to do with t. And so we'll take the partial derivative of this thing. When we do that, maybe we won't spend so much time on the calculation, but by the chain rule and treating x like a constant, this is what term pops out. And this e to the negative t squared times 1 plus x squared all over 2, it remains the same because e to the x is its own derivative. Okay, so some observations here. We have a 2 here. I didn't mean to do that. And a 2 here. We have a 1 plus x squared here, and a 1 plus x squared in the denominator. We have 2 upstairs, 2 downstairs, and the same for 1 plus x squared. We can cancel them. Farewell. So all that we're left with, the term that popped out of the chain rule, is this negative t here. We pull it out because the integration is with respect to x. T is a constant in terms of x. We can pull the t out, negative t. So we're left so far, I prime of t is this integral. Then we can distribute the negative t squared in the exponent as follows, and then use our properties of exponentials to split it up into e to the negative t squared over 2 times e to the negative tx squared all over 2. And this is what we get. Now, okay, the parametrized integral didn't look so familiar, but this looks at least semi-familiar. Does anybody see how does it relate to our original integral? It looks somewhat similar. In our original integral, I'll go back, e to the negative x squared over 2. Now we have e to the negative tx squared over 2. So now there's just a t thrown into the mix. What we're going to do is make a substitution. The change of variables y equals tx. And when we carry this out, this is what we get. We get the I prime of t is equal to e to the negative t squared over 2 times this integral, which is actually our original integral that we're trying to compute. We have it here in y. We originally had it in terms of x, but it's no big deal. They call it dummy variable. Thank you for the chat. There's something you should be very suspicious about that I haven't mentioned. This is not our original integral. I've actually lied to you. It's half of it. The bounds are different, yes. Good observation. This is from 0 to infinity. Our original integral was from negative infinity to infinity. How are we going to help ourselves if it's not the same. It's not the same, but it's not too far different. You can see the symmetry of the bell curve. What we're going to do is compute half of the integral. We're going to compute this area, and then we're going to double it to get the whole thing, which corresponds to our original integral. Okay, so thank you for that. So what we have so far, we have the parametrized integral that we define. We show that its derivative in terms of t is equal to negative c. C is this thing, or half of the original Gaussian integral, times e to the negative t squared over 2. I want to emphasize, it really does seem in a way like we were just making things a lot worse, but I promise we'll get somewhere. So what next? This is where the fundamental theorem of calculus comes in. So for b bigger than 0, I want you to zone in. There's a lot here. I want you to zone in on this middle expression, okay? The integral from 0 to b of I prime of t with respect to t. We're going to compute that in two different ways. The first way is using the ordinary fundamental theorem of calculus. You take the antiderivative of I prime, which in this case is exactly I, and evaluate it at the endpoints, which in this case are b of 0. So that's how we get this side. The other way that we're going to do it is we're going to substitute in our expression for I prime of t that we found above by using differentiation of the integral sign. So when we do that, we put in the integral from 0 to b of negative c e to the negative t squared over 2. I think this negative c is a constant. It's the value of this integral, but it's a constant. It's a number. So we can pull it out. It has nothing to do with t. We're left with negative c times the integral from 0 to b of e to the negative t squared over 2. We're integrating with respect to t. Now, okay, I of b minus I of 0. Ignore I of b for now. We're going to look at I of 0. What happens when we plug 0 in for t here? We get e to the 0. So it's 1. I of 0 is the integral from 0 to infinity of 1 over 1 plus x squared with respect to x. As we talked about before, we use the fundamental theorem of calculus. The antiderivative of that is arctangent of x. When we do the evaluation at the limits, we get pi over 2 minus 0. It's pi over 2. So this I of 0 is going to become pi over 2. I of b minus pi over 2 is equal to negative c times this integral. Now, the integral here is not our original one, but it's close. Let's see, our original one is from 0 to infinity. Well, that's half of the original, so I misspeak a bit, but you get the idea. And this one is from 0 to b. This is what we have so far. It's kind of a lot, but we'll work through it. We've established that I of b minus pi over 2 is equal to negative c times the integral from 0 to b of e to the negative t squared over 2 with respect to t, where c is half of the original Gaussian. And what we're going to do is in this box, look, we'll let b go to infinity. Now, as b goes to infinity in I of b, it's the same, think, as t going to infinity in I of t. What happens to this integrand as t goes to infinity? Negative t squared goes to quite positive infinity. No, excuse me, quite negative infinity, because it's negative. And so it's e to a very big negative number. It goes to 0. So we're going to say that I of infinity, or the limit as b approaches infinity of I of b, is equal to 0. So this, as we take the limit, is going to be 0, leaving only negative pi over 2 on this side. But as b goes to infinity on this side, it becomes the integral from 0 to infinity of e to the negative t squared over 2. It's the same as this c, half the original Gaussian. So when we take that limit, we get that negative pi over 2 is equal to negative c squared, where c is half of the original Gaussian. Negative 2 minutes remaining. I'm not even going to make it to my last example. Well, I'll just finish this one. We cancel the negatives, and we get c squared is equal to pi over 2, and we square root it. So we get this. This is not our original integral. We still need to double it. So when we do that, the integral from negative infinity to infinity, which we saw is indeed equal to the square root of 2 pi, and we are done. So I did not mean to go over, but thank you guys for coming. If you have any questions,
Let's all give Nick a round of applause first, if we can unmute. Well, I'm gonna. It's a good talk. Yeah, if anyone has any questions.